Good day, everyone. We are the Team 7 of Chemistry 1, freshmen of Southern Baptist College, taking up Bachelor of Secondary Education major in General Science. For today's discussion, we are going to tackle the one of major classes of chemical reaction, the role of water as a solvent, and the role and nature of water. For our objectives, at the end of the discussion, the students were expected to first to differentiate the three major classes of chemical reaction, second, examine the role of water as a solvent, and lastly, to describe the whole nature of water. Let's start our discussion with the first major chemical reaction. And there are three major classes of chemical reaction. First, we have precipitation reactions, acid-base reactions, and oxidation, reduction, or redox reaction. Now let's talk about precipitation reaction. What do we mean by precipitation reaction? It is when two soluble ionic compounds in aqueous solution mixed, ion exchange will take place, such as AB plus CD is to AC plus TB. If one of the product is insoluble in water, it will come out of solution as a precipitate. Let's take a look for some example of precipitation reactions between salt and lead and salt in aqueous solution. Lead nitrate or Pb and O3 and potassium iodide Ki react to form potassium nitrate KNO3 and soluble in butane. We have the second major class of chemical reaction, which is acid-base reaction. What do we mean by this? What is an acid-base reaction? First, let's define the acid and bases. An acid is a molecule or solution that contains a lot of hydrogen ions or H+. Acids like to donate hydrogens to the other compounds. Acids are usually taste sour, just like lemon juice or vinegar. While bases are molecules or solutions that are low in hydrogen ions. They like to grab hydrogen off of other compounds. Bases usually feel slippery, just like soap. Now let's talk about salts. Salts are neutral compounds, which means they have no charge, and they are the result of an acid-base neutralization reaction where acids and bases react to yield water and a salt. NaCl is the type of salt that you use to season your food.
Acid-base reactions are the chemical reactions that occur when acids and bases are mixed together. The Bronsted-Lowry theory of acids and bases discusses them in terms of the exchange of hydrogen ions. Take a look at the illustration. As a result of such a reaction, you end with a conjugate acid and a conjugate base.
Acid-base reaction. Simple acid-base reaction involve the transfer of a hydrogen atom from the acid to the base. Example, HCl plus NaOH is to H2O plus NaCl, where HCl is acid, NaOH is the base, H2O is water, and NaCl is salt. Next, we have HCO3 negative plus HO is to H2CO3 plus OH, where HCO3 negative is the base plus HO being acid
and H2CO3 being conjugate acid and OH being conjugate base. In most acid-base reactions, there will always be water and the salts. For example, hydrochloric acid HCl reacts with sodium hydroxide NaOH to form sodium chloride NaCl salt and water H2O.
And lastly, we have oxidation reduction or redox reactions. What is oxidation reduction reactions? An oxidation reduction reaction is any chemical reaction in which the oxidation number of a molecule, atom, or ion changes or gaining or losing an electron. Redox reactions are common and vital to some of the basic functions of life, including photosynthesis, respiration, combustion, and corrosion or rusting. The oxidation state or OS of an element corresponds to the number of electrons, E negative, that an atom loses, gains, or appears to use when joining with other atoms in compounds. Example, CuS plus 2AgNO3 aqueous is 2AgS plus CuNO3 2 aqueous. Take a look at the illustration.
The role of water as a solvent.
What is water?
Water is called the universal solvent because it is capable to dissolving more substances than any other liquid. This is important to every living things on earth. It means that wherever water goes, either through the air, the ground, or through our bodies, it takes along valuable chemicals and mineral and nutrients. It is water chemical composition and physical attributes that make it such an excellent solvent. Water molecules have a polar arrangement of oxygen and hydrogen atoms. One side, hydrogen, has a positive electrical charge and the other side's oxygen has a negative charge. This allows the water molecule to become attracted to many other different types of molecules. Water can become so heavily attracted to a different compound like salt that it can disrupt the attractive forces. Water molecule diagram. This diagram shows the positive and negative part of a water molecule. It also depicts how a charge such as an ion, nickel, and fluoride, for example. Why salt dissolves in water? At a molecule level, salts dissolves in a water due to electrical charge and due to the fact that both water and salt compounds are polar, with positive and negative charge on opposite sides in a molecule. The bond in the salt compounds are called ionic because they both have electrical charge. The chloride ion is negatively charged, and the sodium ion is positively charged. Likewise, a water molecule is ionic in nature, but the bond is called covalent, with the two hydrogen atoms but situating themselves with their positive charge on one side of the oxygen atom, which has a negative charge. When salt is mixed in with the water, bond of salt dissolve because the covalent bond of water are stronger than the ionic bonds in the salt molecules. The positively charged these sides of the water molecule are attractive to the negatively charged chloride ions, and the negatively charged sides of the water molecule are attracted to the positively charged sodium ions. Essentially, a tug of war ensues with the water molecules winning the match. Water molecules pull the sodium and chloride ions apart, breaking the ionic bond that held them together. After the salt compounds are pulled apart, the sodium and the chloride atoms are surrounded by the water molecule. As this diagram shows, when this happens, the salt is dissolved, resulting in a homogeneous solution.
Thanks to its ability to dissolve a wide range of solutes, water is sometimes called the universal solvent. However, this name isn't entirely accurate since they are some substances, such as oil, that don't dissolve well in water. Generally speaking, water is good at dissolving ions and polar molecules, but poor at dissolving nonpolar molecules. A polar molecule is one that's neutral or uncharged, but has a symmetric internal distribution of charge, leading to partially positive and partially negative charge. Water interact differently with charged and polar substance than with non-polar substance because of the polarity of its own molecules. Water molecules are polar, with partial positive charge on the hydrogens, a partial negative charge on the oxygen, and a bent overall structure. The unequal charge distribution in water molecule reflects the greater electronegativity or electron greediness of oxygen relative to hydrogen. The shared electrons of OH bonds spend more time with the O atom than with the HS in the image below. The partial positive and partial negative charge on water molecules are represented by symbols. Start superscript plus and superscript. Start superscript minus and superscript respectively. Because of its polarity, water can form electrostatic interaction, charge-based attraction, with other polar molecules and ions. The polar molecules and ion interact with the polarity positively and partially negatives and of water, with positive charge attracting negative charge, just like the positive and negative ends of magnet. When there are many water molecules related solute molecules, as in aqueous solution, this interaction leads to the formation of a three-dimensional sphere of water molecules or hydration shell around the solute. Hydration shell allow particles to be spread out evenly in water. How does the formation of hydration shall cause a solute to dissolve? An example, let's consider what happened to ionic compounds such as table salt NaCl when it's added to water. If you stir table salt into water, the crystal lattice of NaCl will begin to dissociate into Na. Starts superscript plus and superscript. Stars superscript minus and superscript ions. Dissociation is just a name for the process in which a compound or molecule breaks apart to form ions. Water molecules form hydrogen shell around the ions positively charged. Start superscript plus and superscript ions are surrounded by partial negative charge from the oxygen ends of the water molecules while negatively charged. Start superscripts minus and superscript ions are surrounded by partial positive charge from the hydrogen ends. As the process continues, all of the ions in the table salt crystal are surrounded by hydrogens shell and dispersed in solution. Non-polar molecules like fats and oils don't interact with water or form hydration shell. These molecules don't have region of partial positive or partial negative charge, so they are electrostatically attracted to water molecules. Thus, rather than dissolving non-polar substance such as oils, stay separate and form layers or droplets when added to water.
The polar nature of water.
Water has a simple molecular structure. It is composed of one oxygen atom and two hydrogen atoms. Each hydrogen atom is covalently bonded to the oxygen via a shared pair of electrons. Oxygen also has two unshared pairs of electrons. Thus, there are four pairs of electrons surrounding the oxygen atom. Two pairs involved in covalent bonds with hydrogen and two unshared pairs on the opposite side of the oxygen atom. Oxygen is an electronegative or electron-loving atom compared with hydrogen. Water is a polar molecule, meaning that there is an uneven distribution of electron density. Water has a partial negative charge near the oxygen atom due to the unshared pairs of electrons and partial positive charges. An electrostatic attraction between the partial positive charge near the hydrogen atoms and the partial negative charge near the oxygen results in the formation of hydrogen bonds as shown in the illustration. The ability of ions and other molecules to dissolve in water is due to polarity. For example, is the illustration below. Sodium chloride is shown in its crystalline form and dissolved in water. Many other unique properties of water are due to the hydrogen bonds. For example, ice floats because hydrogen bonds hold water molecules further apart in a solid than in a liquid, where there is one less hydrogen bond per molecule. The unique physical properties, including a high heat of vaporization, strong surface tension, high specific heat, and nearly universal solvent properties of water are also due to hydrogen bonding. The hydrophobic effect of the exclusion of compounds containing carbon and hydrogen, nonpolar compounds, is another unique properties of water caused by the hydrogen bonds. The hydrophobic effects is particularly important in the formation of cell membranes. The best description is to say that water squeezes nonpolar molecules together.
Covalent compounds may be further classified as apolar or nonpolar. When the combining atoms differ in electronegativity, their bond is polar. One atom tends to pull the shared electron more towards itself, and that atom acquires a partial negative charge. One side becomes denser in electron than the other. This creates a partial positive charge on the less electronegative atom, and a partial negative charge on the atom on the more electronegative atom. This is the case of hydrogen chloride. HCl is more electronegative than hydrogen. The electronegative of chloride is 3.0, while that is hydrogen is 3.1. When all bonds are polar covalent, the molecule is not necessarily polar. Not only the types of bonds present influence the polarity of a molecule, but also its shape. What about the molecule? This molecule has bent structure. Its HOH bonds angle is about 100 degrees Celsius. 100 degrees. Because of its bent structure, the molecule is electrically unsymmetrical and thus polar. A molecule assumes the shape that will place the atom bonded to the key. A molecule with a polar bond may not necessarily be a polar molecule. A polar molecule exhibits a dipole or partially positively charged and negative charge. Hence, the polarity of a molecule with the polar bonds depends on the spatial distribution of the polar bonds. If the polar bonds cancel each other, the result is non-polar molecule. For example, carbon dioxide is CO2 has polar bonds, but its linear arrangement makes it non-polar. Water and chloroform are polar molecules. When the two hydrogen atom bonds with the oxygen, they attach to the top molecule, rather like Mickey Mouse's mouse ear. This molecule structure gives the water molecules polarity, or a lopsided electrical charge that attracts other atoms. The end of the molecule with the two hydrogen atoms is positively charged. The other ended with hydrogen negatively charged, like a magnet, when north pole are attracted to the south pole. The positive ends of the water molecule will connect with the negative end of the other molecules. What those means of water polarity, it allows to dissolve other polar substance very easily. Then a polar substance it is put in water, the positive ends of the molecule are attached to the negative ends of the water molecules, and vice versa.
Before we end, I am going to give you a few words to ponder. There is no end to education. It is not that you read a book, pass an examination, and finish with education. The whole of life, from the moment you are born to the moment you die, is a process of learning. That is according to Jiddu Krishnamurti. I am Kay, and work with us as we dig deeper in chemistry.